Okay, my name is Matthew Donahue. This is Fluid Mechanics Project 3, simulating inviscid flow, laminar viscous, and turbulent viscous flows. My partner is Noelzy. I'm going to start off with doing the inviscid flow. First things first, as per usual, make sure we switch to 2D as we are working with 2D cases. And we're going to use a 1 diameter circle with a 50 by 50 meter box for our profile. Or we're going to do a 10 meter by 10 meter box, just for example. So we're going to switch to our z-axis and start our sketch. Or you're going to do the 50 actually. Just that way it's large enough where we can actually have a profile. There we go. Now everything is dimensionalized so we have symmetry and everything's even. We can go ahead and create our surface. And press generate. There we go. See, we get our circle in the center. This way we have plenty of room for a overall structure. Now we're going to go ahead and do our mesh. We're going to make sure we create a fine enough mesh around our circle where we'll be able to actually see um, the correct contours and patterns and everything and collect the right data. I'm only going to do the meshing and the geometry once, then I will just be copying everything just to save time on as much as possible. Alrighty. So first thing we're going to do is go ahead and name all our different sections. This will be our inlet. It's going to be velocity inlet. And then we're going to create our outlet, which will be a pressure outlet. And then we're going to multi-select these two parts because this will be called our symmetry. And then we're also going to select here to just create the wall for our cylinder wall. And then we go ahead and we're good with just those 4 named sections. Next thing we're going to do, we're going to go click mesh, come up here. We're going to do a method, just like this. Apply our geometry, and we're going to switch it to a triangle method. And press generate. So we have this now, we have this profile for our mesh started out. We're going to insert a sizing mesh. We're going to pick our circle. And we're going to do 250 divisions on our meshing here. Make sure not to capture curvature, and it is a hard body meshing. And we're going to press generate. You can kind of see we're now getting this kind of concentrated area there. Next thing we're going to do is we're going to do an inflation. So we're going to pick this as our face for the inflation, and the boundary is going to be the cylinder wall. And then we're going to go by first layer thickness. We're going to do 3e to the 3 for our first layer height with a maximum of 150 layers. So then once we're done, if you do a smaller box, your meshing will be the whole box, but because since we're doing the 50 by 50 box, it won't be able to reach out, and you can make it bigger. But ideally for what we're doing, this will be plenty good. So After we've done that, we've named our sections. Go ahead and we can close out of this and out of this one. And we can update our geometry. There we go. So now we can go into our setup and actually start putting everything in. In the directions, we were specified to use a 5 meter per second velocity for the inviscid case. Let me just drag this over to the correct screen. So real quick, while this is still loading, we're not going to touch any of our values here, any conditions here. We're going to keep those same as they are shown right here. As with every case, we're going to go straight to our model and we're going to go to the viscous. We're going to switch it to inviscid since this is the type of flow we want. There we go. Go ahead for air. We're going to use a density of 1 because it's inviscid flow. We don't have to worry about that viscosity because essentially we'd have a very, very small Reynolds number. Next, we're going to go to our boundaries. We're going to go to our inlet. We're going to choose that 5 meters per second. We don't need to really touch or edit any of our other boundary conditions for this one because with the model already selected and we have our velocity, we mainly have everything done. So next thing we're going to do is go to our reference values. We'll make sure to put this from our inlet to the surface body. And then also go to our results. We're going to change our residuals to get a higher accuracy in our data. We're going to add 2 zeros. There we are. Next thing we're going to do is we're going to go to methods. This will make it where your overall values will be a little bit better, a little bit more, it'll be a bit easier to get everything. So we're going to pick simple and go down to pressure and we're going to choose presto. Once that is done, we can go to our initialization. More settings. We're going to switch this up to 25 iterations and apply that. And then we can go ahead and initialize. Then for our calculations, we're going to just, for this instance, you can run however many you want. I'm going to run 200 just that way it doesn't take as long to process everything. There we go. Now that we've done that, we can go ahead from here. We can go ahead and select our XY plot. And we want the pressure coefficients. And we're going to do it off our cylinder wall with a direction vector. Or I think it's this one. Give me a second. Okay, so the issue was I put the iterations and profile updating rules. Now once we calculate, it should calculate correctly. There we go. So now when we come down this XY plot and you do the direction vector, save and plot, you should get a nice parabolic function for that pressure coefficient curve. As you can see, we kind of with the inviscid flow, as we move left to right, we slowly decrease and then come back to the pressure we need to go to. Next up is the velocity. You change this to velocity, and then you would do the same thing, and you're going to get a inverse parabolic function or half circle, and you should get this is the general shape for an inviscid flow. Next thing we're going to do while we're here in the setup section is we're going to go to do reports, go to forces, select the cylinder wall, and print it out. And you can see here forces pressure, that is our drag force. Coefficient is our drag coefficient. So your values for this should be near 0 or basically very small values because you shouldn't really get one. There should be very little drag in this scenario. So next thing we're going to do, because we're done there, There we go. Now that we're done there, we can go ahead here to our results portion. We're going to go ahead and also name this Invisid. Okay, so now we can go ahead and go to our results page, which is pulled up here. Go ahead here. And now we need to do our streamlines and our contours. So first thing we can do is contour 1 will be our velocity contour. Or you could just call it contour 1. This will be our pressure 1. We're just going to call it C1. Do 110 contours and make sure it is on symmetry 1. Apply. And you should get contour where you can see your maximum pressure at the front end and back end of your circle or your cylinder. This is where you're going to see your highest pressures, and you should see the lowest pressures and then the upper and lower regions due to the higher velocity. So now we're going to go ahead and add in our second one. Go C2. And then this one's going to be 110, but we're going to switch that to velocity and symmetry 1. Going to pull out contour 1. As you can see, our velocity is lowest here, highest at the top. And the last thing we're going to show is the streamlines. I'm going to go up here to this button, press it. It's going to enter your streamline. You want to start from your inlet, and you can do equally spaced vertex, preferably equally spaced, and then I'm going to do 2,500 number of points just so you can actually see it. And there we go. We get the correct velocity profile for this kind of flow. Now that we've finished this flow, we're done with our Invisid case. So like I mentioned, we're going to just go ahead here. We're going to duplicate just so we don't have to recreate the meshing and the geometry. So then once we come here, we're going to go to our setup again. And now we're going to set for the laminar flow. And give that a moment to load. There we go. It's loaded. So we can go to our model, switch this from Invisid to laminar. And then we go to materials, go to our air. We're going to keep that air at that constant value of 1. But we're going to go ahead and change our viscosity because now that we're not in a viscid flow, we're using viscosity now. So we're going to use a viscosity of 0.05 because for this, we want a very small Reynolds number. This way we can that's just the conditions because our transition region is that close around that 500,000 mark, but we're going to show an extreme. We're going to go ahead there, and then we're going to our boundary conditions, go to our inlet, and we're going to change this now to a velocity of 1. Let me just double check. Make sure I put 1 too many zeros, just 0.05. There we go. Make sure our reference values, inlet to surface body, methods will be the same. I mean, you can keep them back to coupled. And then we're going to go ahead and to make sure our initialization is correct. Initialize. We're going to run our 200 calculations again. There we go. And then we can come back down here to our plots. Click on this one just because it's here because we duplicated it. We're going to go ahead and repeat our process another bit. In this case, you would press right to file and then save it as a Excel file to then export it. So that way you can compare all three data sets. And just like that, you're going to get that nice function that you should get for the loss or for the pressure coefficient. Or this is static pressure. Let me set the pressure coefficient. Pressure coefficient, we're looking for this kind of like little scoop. And then it can, as you would go, it would go out and kind of flatten out a little bit. So then next, we're going to go do our velocity. And you'll notice it's a straight line because of the no slip condition. Since we're taking our reference as a cylinder wall, once we hit that wall, it's like we're measuring the velocity on that wall. Because of no slip condition, we're going to get either very small velocity because there's a little bit of roughness to our structure, or we're going to get zero because of that. So it's going to look constant. And then we're going to go here for reports, go back to forces, and we're going to choose our wall, print, same thing here. As before, we're going to see we get our force value, and then we get a coefficient value. I have had some issues with the coefficient values being a little bit off in ANSYS, so usually it's good to double check these with hand calculations. Usually the pressure force has been pretty accurate, but otherwise than that, it has not been extremely accurate. And then we're going to go ahead and we can go ahead and take a look for our contours and stuff. Now I will specify you should have a higher drag force for your laminar flow than your turbulent. As you can see here with our streamlines, we're kind of experiencing that where we're getting that little bit of a wake region here. It should be much larger, but I think due to the fact we have such a small velocity, we're getting a very small wake region. And this is for our streamline. When we show the contour, we should be getting more of a wake region. So just to try and get a better shape on this, we're going to go ahead and change some things with our setup, because I feel like that doesn't really do a very good job of showing off a laminar profile. So double check everything. So what we're going to go ahead and do, we're going to change our viscosity here to 0.01, because we're going to go for a Reynolds number of like 1,000. So we're going to keep that density the same. Then we're going to go boundary conditions, go to our inlet, and we're going to use 10 meters per second. And then once you've done that, everything else, just double check all your stuff. And then you can go ahead and initialize and run your calculations. And once we plot again, for velocity, we'll get that constant line. For pressure, we're going to get cylinder wall. You can kind of see it. We get a goofy shape now that we've changed some of our values, but still kind of has the same shape, but we're going to kind of scoop down and then level out. My bad. Share the screen. Okay, so just fixed up our number to make our Reynolds number a little bit smaller, but now we're getting the correct shape for that pressure coefficient. Along with when we look at that velocity, we should still have that straight line because, like I mentioned, no slip. And then we can go ahead out here and we can update this system. And we should have a profile that looks a lot better for our case. There we go. Now we're seeing that wake region that we're supposed to be seeing with the laminar case. Then once we go to our contour, same thing for our velocity. And then even for our pressure one, we're kind of seeing that generalized wake region in the back. So that's a better way to look at it. There's a little bit better. This time we went for Reynolds number 120. We used 0.083 for our viscosity and kept the 10 meters per second. This way we got a little bit better profile for the visuals. All right. So now that we've done that one, we can now move on to our final case, which will be our viscous turbulent flow. We're going to go ahead and duplicate it again. And then we're just going to label this laminar. And we'll just call this one turbulent. Okay, so like I mentioned, we're just going to go straight into setup because we're going to use the same meshing and geometry as the first two cases. But this time we are going to change some things a little bit differently. We're going to have a much larger Reynolds number now, which means we're going to use a much smaller viscosity. We're going to keep the same constant 10 meters per second velocity, but we're going to use a much smaller viscosity because we want to get a Reynolds number of 2 million. So we're going to have 5 e to the negative 6. First things first, go to models, and we're going to go to viscous. Anything past laminar is going to be more or less what you're going to be using. These equation ones are what you're going to use for turbulent. For our case, we don't really need to go above the one equation one, and we don't really need to do anything. Just switch that to that model. Materials, go to fluid. We're going to change our viscosity real quick. And we're going to go ahead and we're going to add on our changed viscosity. We're going to keep the same density. And this is going to give us a Reynolds number of 2 million, which is an extreme case, which is perfect for what we want. Make sure our inlet velocity is still at that 10 meters per second. There we go. We don't need to touch anything else. Methods are, we're going to leave them like this in this instance because it tends to get better data when we go this way. And we're going to initialize. We're going to run our calculations. You'll notice you'll have another value here. That's just that extra equation that's going to be simulating the turbulence. And we're going to be looking for a similar profile where we're going to have a wake region, but our wake region should be more narrow. There we go. So we're going back down to plots, X, Y. We're going to start off with our pressure coefficient. And there we go. We're going to get a dip that's going to come back out and level out. And then same thing, like with our previous case, we're going to have a straight line velocity due to the fact of no slip condition. That's just how ANSYS is picking it up. And then we're going to go down here again, go to our force reports. Like I mentioned, we should see higher force number, which we are. And then our pressure coefficient is actually smaller than that. So the pressure coefficients tend to be a little bit different than what's calculated in ANSYS. So I would double check all those values with your hand calculations. But this is a good way to get like your force to then go ahead and calculate your pressure coefficient. And then we can go ahead and click out of here. and we can go to our results tab, and we can see the difference in our contours and streamline. Like before mentioned, with all those graphs, you would write to file to get the data from there so that we can compare them between all three cases. So as you can see with our contour here, for our pressure, we're going to see a maximum here. We're not going to see in the back because we're going to have that wake region, but we're also going to see it kind of smooth out towards the top in terms of pressure. With our velocity, we're going to see a low velocity at the back and front, but we're also going to see that more narrow wake region now, which is what we want to see from turbulent, because since there's higher energies within the particles, we're going to see them kind of close down a lot more. And then finally, our streamline, we see the same kind of profile going on, which is what we want to see. This is with a Reynolds number of 2 million. And that should be everything for the project demonstration. Everything else is stuff you usually just will export by writing out the file, and then you could do it in Excel. That's all for this project.